Let us now speak about backward induction, and backward induction can be viewed as a way of computing the subgame perfect equilibrium of a game. It's a procedure that's used widely, or variants of it are used widely in game playing programs, be it chess or other ones. And how does this work? So this is a busy slide, and don't be daunted. We'll explain it leisurely. Also, some of you may have not seen algorithms before, but we'll explain the algorithm in very plain terms. Before we do, let's just first give the intuition, and the intuition is very straightforward. What we're trying to do is associate a value of the game not only with leaf nodes. With leaf nodes, we know what the value is. It's simply defined by the payoff vector associated with the leaf node. It's part of the game definition. But suppose we want to go to the root of the node or any other internal node and say, so what really is the payoff associated here, assuming that agents will play a subgame perfect equilibrium? And that's the goal of this procedure called backward induction. And the intuition is very straightforward. We'll go to the leaves and back up slowly at every step of the way, assuming the agents will take an action that maximize their payoff at that node. And so that's the intuition. Now let's see how it's done formally. The procedure is called backward induction, and it takes one argument, a node in a tree, any node. Could be the root, could be a leaf, or anything in between. And of course, every node has some player associated with it. And just anticipate what we'll encounter shortly. Row of H will be the player associated with that node H. And when the procedure returns, it'll give us those payoffs to all of the agents associated with that node. So how did that work? And again, remembering our intuition, we say the following. If H is a leaf node, Z is a set of leaf nodes. If H is a leaf node, then we simply return the payoff vector as defined by the game. That's where the recursion bottoms out. Most of the work, of course, happens in the recursive step when we're not at the leaf node. So for that, we do the following. We will keep a variable called besutil, and besutil will be a vector of payoff associated with the agents, each one with each agent, and we will be updating that vector as we go along. So to start out with, we'll assume the payoffs are all terrible. Let's call that minus infinity, a payoff smaller than all possible payoffs in the game. And then we do the following. We will look at all the actions available at that node. So chi of H is a set of all actions available at that node. A would be an example of such an action. So we'll take each action in turn, one at a time, and do the following. We will look at the child you reach by taking action A at that node H. That's called sigma H of A. So sigma of H of A is simply another node, one of the children of node H, that you arrive at by taking that particular action A. And we'll recursively look at that vector associated with that child, and we will keep it at this variable called util at child. So we have two vectors, notice, besutil and util at child. Besutil is the best we found so far, best for a particular agent, and util at child is what we found at a particular child. We'll be going over all the children one at a time, and if ever the util at child is better for the agent than the best util so far, we'll update the best util. That's what's going on here. So this is what this says. It says util at child is a vector. So look at the element of that vector corresponding to the agent we care about, the agent in node H. If the util at child is better for that agent given the best util, what we found so far, then simply update it. Update best util to be this util a child. Otherwise, leave it unchanged. And so in this way, we're cycling through all the children and finding from that agent that to whom node H belonged, from his point of view, which of all the vectors are best. And again, the intuition is he will take the action leading to that child and updating that vector accordingly. And that's why when we're done, we're returning the best we found so far, called best util. That is the backward induction procedure. And notice that we don't return a strategy, just return the list of payoffs. And in some sense, it's you can think of it as simply extending the payoff from the nodes to all internal nodes. But even though we don't explicitly return the equilibrium strategy, the one that will be subgame perfect, it's easy to read it off those numbers, because at every node, the agent will take the action that leads it to the node, the child node, with the best utility from his point of view. So that is the subgame perfect. That is a procedure for computing subgame perfect equilibria, the backward induction. And if we look at the special case of zero-sum game, it's simplified a little bit, because then there are only two players, and the payoff for one is minus the payoff to the other. So really, we only need to keep track of one number associated with each node. And so there's less bookkeeping to be done. And furthermore, in such zero-sum games, and all win-lose games are zero-sum game, for example, chess, there is a way to speed up the backward induction procedure. By the way, in the zero-sum game, we simply call it the minimax procedure, because we alternate between minimizing and maximizing the value. One player wants to minimize it, the other to maximize it. And in fact, there's a way to speed up the procedure, and we won't go into it here, but the intuition is that as you're visiting a certain children of a given node, you may find out that at that point there's no need to explore the remaining children of that node, as we did in the backward induction procedure, because intuitively it won't matter. You've already found a value that means that this node that you're examining, the parent node, will never be visited. And it's called the alpha beta pruning procedure, an optimization of the backward induction or the minimax procedure for zero-sum games. And you are invited to explore it elsewhere. There's one more thing I want to say in connection with backward induction and in fact with subgame perfection. And there's sort of two different things here, and they're all keyed off the same example, the famous example of the centipede game. So this well-known example, you have two players, they alternate turns. We have player one moving, and then player two moving, and then player one again, and player two, and so on and so forth. But the payoffs are constructed in a contrived way so that they're gradually increasing, and you can imagine, it's called a centipede because you can imagine rather than have only 5 legs here, you'd have 100. They slowly rise so that the payoffs here are much smaller than the payoffs here, and indeed very much so if you keep going. But even though they rise, they are contrived in a way that lead to only one subgame perfect equilibrium. Players will defect in every place. Their payoff will go down in every place here. So the only outcome, subgame perfect outcome, is this one, where the first player defects immediately, goes down immediately, which is, of course, similar to the prisoner's dilemma, is a little counterintuitive, because had they only had the good sense to keep going, they would have gotten something in the ballpark of this or this, both of which are much better for both than here. But nonetheless, when you examine it, you see that there's only one subgame perfect equilibrium here, and in fact only one equilibrium outcome, namely this one. And you can see it by doing again the backward induction procedure. If the game progressed and in fact reached this node, what would player 1 do? Well, they would go down getting a 4 rather than a 3. But player 2 knows this. So knowing that player 1 would go down, he'd rather go down because he'd get a 4 rather than a 3. Similarly here, player 1, knowing that player 2 would go down, elects to go down here because they would get 3 rather than 2, and so on. And this is really the backward induction argument. So on the one hand, clearly a clear account of what will happen in this game. But there are two problems. One of them is sort of simply experimental and common sense, and the other is more theoretical. On the pragmatic level, common sense simply tells you this is not what's going to happen. The players will cooperate for a while until at some point, in fact, somebody would go down and end the game. They know there's so much to gain by going forward, they would, if you wish, take the chance. And this intuition is borne out repeatedly in experiments. People do cooperate for a while until, in fact, eventually they defect. So that's a problem for theory. But there's also another problem that's theoretical in nature. So we know that the only subgame perfect equilibrium is one where agents defect, go down at any point in time. Now imagine that the game starts and player 1 goes across, does not go down. What does player 2 do? Well, on the one hand, you could say, well, the only subgame perfect equilibrium is to go down. They should go down because they'll go through this backward induction argument and it'll tell them that the best thing for them is to go down. But that same argument told them, player 2, that player 1 would have gone down right off the bat. But they didn't. So maybe they won't go down again. But what will they do? And fundamentally what happens here is you have an event of going across that the standard theory tells you will happen with zero probability. How do you condition on an event that had a zero probability prior? There's a big literature on this. It's a very interesting, deep issue in game theory. We will not delve into it any deeper, but it's interesting to note it.